All right, so here we're going to talk about how we represent polymers when we draw them out and when we want to name and identify them. So a generalized diagram of a polymer looks like this. It's a little bit different than structural diagrams we have seen before. Key thing we have is we have the square brackets on either side. So because a polymer is a repeating unit, when we draw a polymer, what we actually do is we don't try to draw the entire thing, because this literally can be hundreds or even thousands of carbons long. Instead, what we draw is we draw a segment of it, and typically we draw 3 repeating subunits as part of that segment, although sometimes there's more, sometimes there's less. It's perfectly valid to also draw this polymer to look like this, which is only a single subunit long. But the idea in both of these diagrams is the square brackets is representing the boundary where it continues on, and you actually have the bond drawn longer than you typically would in order to represent that this chemical continues on outside of the subunit or outside of the shown diagram. We also have the N that is written in the corner as well. This is the same N we use in math. It means number. Treat it similar to X. So this particular polymer is made up of repeating chains that look like this, and it goes on for N number of times. What is N? Well, it could be 1, it could be 2, it could be 30, it could be 500. It depends on the specific molecule that we're talking about and the context it is in. Okay, so how do we figure out what this chemical is called? All polymers are named based off of their subunit. So first thing we have to do is we have to identify what is the monomer that goes with this polymer. And what you want to look for in that is repetition. Now, we see that there's no oxygens involved with this. There's no oxygen bridges, there's no ester, so we know this isn't a polyester, which means it had to have been made through an addition reaction. So this is an example of addition polymerization. What you have to remember with addition polymerization, if I can spell it right, is that addition polymerization is always based around double bonds and triple bonds. So there will always be a 2-carbon base. So what we can actually do with this is we can break this down into 2-carbon chunks. So each 2-carbon chunk is going to represent 1 monomer subunit in an addition polymerization. So we know for this polymer that everything attached to that 2-carbon chunk is part of that subunit. So this is the base that the monomer was made out of. Now, sometimes there will be more than 2 carbons in that. We can actually see 3 carbons here for that exact reason, because we have branching here. And it is possible to have branching on both carbons. But you'll notice there's a repeating pattern here. We have the 3-carbon motif repeating again and again. So that is the other key thing to look for. You do know that the monomer is going to be made of a 2-carbon backbone, but if you forget that, just look for the repetition and chunk it up based on that repetition. Okay, so how do we tell what this was made out of in the first place? Well, now that we see, okay, this is the motif that we're dealing with, we can actually turn that into this. This diagram is going to look a little bit weird, but we've actually seen all of the aspects of this before. Because what's going on here? Well, if you think all the way back to last year, What does a dot represent in chemistry? A dot is an electron. So what we're showing here is we're showing a free radical. A free radical is an unbonded electron. These do not stay stable for very long, and we have basically completely ignored them through the course of chemistry 20 and 30, but they can happen ever so briefly. So the free radical is actually a transition stage in the process of addition reaction, or addition polymerization, or really any addition reaction. So what's going on here is what we're doing when we draw this diagram out is we're actually reversing the reaction. So we know that it had to have formed from this free radical. Well, we know as well electrons hate to be unpaired. They don't like it. So what's the easiest thing for these electrons to do? Well, the easiest thing would be for them to pair with each other. If they pair with each other, it will look like this. We now have a double bond instead of a single bond, and everything is paired up quite nicely. Now, this is a little bit of a weird way to write this. So instead, we'd probably write it like this. And that looks a whole bunch more familiar now. Okay, we have 3 carbons. 1, 2, 3. If we have 3 carbons, what do we start the name with? We start it with prop. We have a double bond. That means it's going to end in -ene. And since this is a 3-carbon chain, there's only one way that we can get a single double bond into this, so we don't need to include numbers. This is propene. So what would its name be? Well, if we go all the way back to this chemical, if we use propene as the base, the name is polypropene. Even though it indicates a double bond at the end because of the -ene, there's no double bonds in this chemical. But that's okay because the poly in front of it means it's already undergone polymerization, and in that process of polymerization, the addition reaction has removed the double bond. So we know that this was the original chemical, and that's what the name gets based off of. What if we want things the other way around? What if we want to draw a polymer? Well, drawing a polymer is super easy. We just have to act out the addition reaction. So we know it's poly to but 2-ene. That means that our monomer subunit here is but 2-ene. So we're going to start out by drawing but 2-ene. We have 4 carbons. We know that the carbon 2,3 is double bonded. Everyone else gets a single bond. And then we have hydrogens coming off the sides. Now I'm drawing all of the hydrogens in here. But when we actually draw out the polymer, we're probably not going to want to do that. So let's condense this down into a condensed formula. Okay, there's our but 2-ene. Now, what we're probably going to want to do to this is we're going to want to bend it so that we have the double bond exposed on its own. Normally, we wouldn't do this with a double bond. This straighter configuration is probably more preferred, but this is going to make our lives easier, so we're doing it. Okay. And it doesn't matter if you put both on the bottom, both on the top. It does actually, it doesn't actually make a difference. It will just change the way that you end up drawing it. Both of the ways of doing it are correct. Next thing we're going to do is we know that addition reaction is going to break up the double bond. So we're going to move the electrons from the double bond out to the edges. No, don't do what I just did automatically and put too many hydrogens on your central carbons, because that's not good. I blame doing this too late at night. Okay, now we've turned this into a free radical. And this is basically what's happening in the addition reaction. The double bond's getting cracked open, it turns into a free radical. And basically all we're doing is we're just allowing that free radical compound to bond with other identical free radical compounds around it. Because those electrons are not going to want to stay like that. Chemicals hate being free radicals. It's not a stable configuration. So what do? They make bonds. So you're going to get bonds forming between these free radicals. And it's going to fuse them all into one compound. And that compound is going to be our polymer. I tend to go in a habit of writing down the square brackets first, but actually you probably don't want to do that. You probably actually want to write out the spine of your polymer first, and then add on the branches so that you size it properly. What you do want to do is make sure, 5, 6, that the square bracket does contain all of the branches as well. It's a little finicky thing, but it makes the diagram look much nicer, and some people are picky about that. Okay, now I've got all my branches in, and one very horrible 3. Better. Next, I'm going to add in my square brackets, indicate bonds continuing outwards, and indicate my N down in the bottom. And this is what polybutadiene would look like. The important thing with this one, and the reason I picked this chemical, is that if you look at it now, it looks like you have 6 subunits, but really you only have 3. So you do have to remember when you're taking a look at polymers that the subunits always have to have 2 carbons in the backbone. And that backbone is the one that goes straight across the diagram. So each one of those subunits is overlapping with the backbone twice, because the addition reaction requires 2 carbons. So don't get tricked into thinking that this has 6 subunits in here, because you need the 2 carbons of the backbone for it to work, which is why we know the base of this is butene.